Morning, guys. Welcome back from spring break. I hope you guys had a really nice time with family. Got some outside time. Enjoyed some of our nice weather days that we had. We're gonna get back into it. We don't have that much left to cover, so we're gonna take our time, cover it slowly. Workload should be a little bit less fourth quarter, but it's still all very relevant material. So chapter 6 is only 3 sections long, but each section is pretty in depth. So we'll take 2 to 3 E-days to cover it. Okay, so the first part of chapter 6, 6.1, is finding the area between two curves, two or more curves, really. So that would be a bounded region that we would either have to find points of intersection for, maybe the interval is given, different things like that. So I just want to warm up with something that we did in chapter 5, where it was just finding the area below one curve on the given interval. And remember that the area is always the space bounded between in these types of problems, the x-axis and the graph. So I typically had you graph them so you can get a visual. X squared, I'm only going to graph the right side of the parabola, even though it does continue. You can use your graphing calculator to get the graph. Actually, I highly recommend that in this chapter, is getting the exact graph that you need with the exact points of intersection and seeing the interval that they give you. So 3 to 5, we treat those sort of like vertical asymptotes. Rough estimation here, this is 3, this is 5. So this warm-up is just asking us to find the area of this space. Remember, in the beginning of chapter 5, we started by estimating with rectangles, okay, and then we got into the exact value by integrating or anti-deriving. The nice thing about chapter 6 is it's all going to be done on the graphing calculator. Your job is to correctly set up these integrals, and then the calculator will do the math for you. Okay, so this problem, the integral would be area, so integral symbol of x squared. Remember, you need your dx from 3 to 5. So putting that in your calculator, let me switch to Desmos. So if you're using Desmos, it's very, very nice to actually use, especially on a big screen like this. If you hit the function button over here on the right-hand side, and then you tap miscellaneous, that bottom left corner, you can see the integral symbol, the antiderivative. So you need your limits of integration. In this case, we have 3 to 5. You want to put parentheses if there are more than one term. In this case, we don't have more than one term, so I can just put x squared. And then I have to go to the letters and type in dx. Without that dx, it would not calculate for us. So you can see that we have 32 2/3, or 0.67 is our answer. Okay. All right, so that's just a review from chapter 5. Chapter 6 will look more like this, 6.1, more like this, where we have two curves, F and G, and our job is to find this tan, or now shaded green region, between the two. Okay, so if I were to ask you what the distance is, I'm just talking distance right now, from here to here, you would tell me, well, I'm going to take the y value, because we're looking at the height of the pink graph, the F graph, and the y value from the g graph, and you would say f minus g. Whatever those y values are, that would give me the distance between. We're going to do that same exact thing for area between these two curves. So you're going to be thinking about what is the top function minus what is the bottom function all of the time. And if we take that top minus bottom, that is sort of like our height, right? And if we integrate it from A to B, the A to B is really like our width. Okay. So remember, we're not doing this by hand, but if we were, the antiderivative process brings back an x. So an x squared would return to an x cubed. And that extra dimension is where the area comes from. Okay. And when we plug in the b and the a, we would be doing plug in the b, minus plug in the a. So the width would naturally come in there. So your job is to identify the top function, f in this case, it's higher on the graph, and the bottom function, g. This is more of what I was just talking us through. This is the textbook notes for it. It's saying that the end goal, which is what I just circled, is equivalent to the total area, which would be the area of f, minus the area of g. So you could, look up top here, you could say, well, you can treat them separately, integral of f minus integral of g, or you can put them into a singular integral, integral of f minus g, as I showed you. And again, it's top, let me write it down here. Top minus bottom in terms of your functions. And the numbers are always going to go from left to right. Small number on the bottom, bigger number on the top of your integral symbol. Those are your limits of integration. Okay? So you're sort of making a box around the space, right? We have our top, we have our bottom, we have our left, we have our right. Okay, so first example. Find the area of the region between the graphs f of x, which is x squared minus 4x plus 10. That's in, I'm going to make it in red on this graph. Again, go to your graphing calculator and put both of these functions in. And then 4x minus x squared should have been in blue. I don't know why the copy of this never shows it. It's right there. Okay. And specifically, we are finding the area between 1 and 3. So those are the limits of integration. Okay. So first we determine which function is above, which is below, or what's on top and what's on bottom. So red is on top here. It has a larger value. Blue is on the bottom here. And when I'm talking about the value right now, I'm talking about the y-coordinate. So at any given moment, red has a bigger y-coordinate than blue in that interval. That might change in different intervals, but for the space that we're looking at, red is above blue. So you could even write it in that fashion. You could say red minus blue if you wanted to help organize dx. Okay. So when we fully set up the integral, though, we of course are going to put in parentheses are really important. You could simplify if you wanted to, but you wouldn't have to. I like putting one large set of parentheses and then individual parentheses for each function. The second set, as we've always known, is more important when we have subtraction in our problem because the subtraction needs to distribute to both of the terms. So inside of our integral is set. It's the red function minus the blue function, the f minus the g. The limits of integration go from left to right, so 1 on the bottom, 3 on the top. So integrate, that can be done by your graphing calculator. So here's up to you. You can type it in exactly as you see it, or you could simplify. Right? We could say, well, this is easier to write as I can go down to a single set of parentheses. I have an x squared minus a negative x squared, or plus an x squared, so I have 2x squareds, minus 4x, so I have minus 8x, and there's no other constant, so plus 10. So there, I just combine like terms through the subtraction. Do that carefully. Make sure that you distribute your minus sign correctly if you're going to simplify here. But either way, you can plug in the original integral that we set up or the simplified. The other nice thing about Desmos is you can see that it reminds you that you need a parenthesis. And it won't calculate here. It's sort of reminding me that I need something else, and it's usually the dx that you're forgetting. So 5 and a third, 5.3 repeated. And that represents this bounded yellow space that I'm coloring in red right now between those two graphs. That's how large that space is in 2 dimensions. Okay. So here I don't give us a graph. Find the area of the region enclosed by these graphs. They also don't give us an interval. But the language saying region enclosed implies that these two functions must intersect, and therefore those points of intersection are going to fully enclose it. So let's go to Desmos and graph x squared plus 2 and 2x plus 5. And now, the region that is enclosed, I can't draw on this screen, right, is the space where it's completely bounded by the function. So I'm seeing points of intersection. I can tap on them. -1, 3, 3, 11. So my interval would go from -1 until 3, the x values of those two coordinates. The y values don't matter so much. In the top function, my line is always above the parabola in that region. Okay, so I'm going to duplicate this graph back onto my notes. I'm actually going to screenshot it. That worked well. All right. So again, this space right here is what we're looking to find. The 2x plus 5, the line, is there. The x squared plus 2, the parabola, is here. So in the region that's fully enclosed, red is above blue the entire time, and therefore our integral would be quantity 2x plus 5 minus quantity x squared plus 2 dx. And our left value, in terms of the x coordinates, is -1, and our right value is 3. Another reason I know that I need the x's and not the y's from those points of intersection is because if I look inside of my integral, I have x's inside of my integral. So therefore, I would need x values as my limits of integration, because remember, eventually those values have to get inputted into your antiderivative. The calculator's doing it for us in this chapter, but we did it by hand last chapter. So they have to match up. If I put y values, it wouldn't make sense. You wouldn't get the correct answer when you evaluate this. Okay, so I'm going to simplify this. -1 to 3. I have a negative x squared, a positive 2x, and a 3. And it's 10 2/3, or 10.67, if I typed it in correctly. Okay. So we've seen a couple of problems where the limits of integration were given, and here was an example where the language implied that the two lines or two graphs would intersect and create their own limits of integration. Okay. So here's a place where you could try this on your own. Go ahead and pause the video. Give this example a try. The limits of integration are clearly given, so you're just graphing the two. You're determining which one is the top, which one is the bottom, or above versus below, and then you are setting up your integral and integrating it. Okay, so pause the video, give this a try on your own. I'll continue to work on this problem here. So the graph basically looks like that. There's not points of intersection anywhere on this parabola in this line. It's just important to know that the y-intercept of the parabola is up at 12. The y-intercept of the line is down at 4. That is what dictates the above and the below. Limits of integration are from -3 to 3. So So you should get an area of 102. Okay, last example for these notes. No different, they just give us functions of an e to the x and 12 minus e to the x. And they tell us that it's bounded by the y-axis. So that's sort of like having, this is our y-axis, 0 as our limit of integration, as one of our limits of integration. So let's graph e to the x and 12 minus e to the x. I think I actually just used that, yep. E to the x. Okay, so that's the space that we need right there. Okay, so the black one, well, I'm covering it in red now, is 12 minus e to the x. And our other one is just e to the x. They said the y-axis, which is right here, Therefore, this right here is the space that we want. And I had found that point of intersection as 1.792, comma 6. So now that I have a nice graph in front of me, I can see that my above, or my top, is the red minus the blue. More specifically, I'm going from 0 until 1.792.
Mom, there's no show movie. So watch it tonight.
And then we go from 12 minus e to the x is red, minus e to the x. Simplified, 12 minus 2 e to the x dx.
Go, go, Power Ranger.
Okay, I'm getting 11.5. Okay. All right, so that concludes day 1. Now, as always, but more importantly this quarter, I want you guys to realize that the textbook homework is completely optional. You don't need to be doing it. You don't need to be scanning and sending to me. The policy is that there's no homework during homeschooling, so therefore there would not be an additional homework grade for this quarter. So these are optional. They're great practice, of course, but there's no need to do them or send them to me. For each of these sections, I plan to post a worksheet and a mini quiz. Now, like I said, this section is going to take 2 to 3 letter days, so 2 to 3 E-days. So we won't see the practice quiz or the worksheet really coming up until early next week, most likely. I'll probably post it by the end of this week because you might be able to do the majority of it by the end of the second lesson. But as of right now, your only job is to really listen to this video, take notes, and do your best to understand as we move through Chapter 6. Chapter 6 is heavily visual, so you might see some different videos that I'm going to post. I might show some kind of object in order to demonstrate what I have. If you recall, there were some projects in my room that were three-dimensional looking. That's the direction that we're heading once we get into 6.2 and then 6.3. For now, that's it for today, guys. Again, I hope you had a wonderful spring break. Welcome back, and